Okay, we're going to go through this problem from the series circuit worksheet. It is number 4 on the back. Using the laws of circuit theory, solve for the total resistance, the total current, I sub t, the current at resistor 1, resistor 2, and resistor 3. Also the voltage at resistance 1, voltage at resistance 2, voltage at resistance 3. Be sure to put your answer in proper engineering notation and use the correct units. Okay, well let's observe what we have. Right now we have a power source of 10 volts. We have a resistor here of 470 ohms, a second resistor of 1.2 kilo ohms, a third of 270 ohms, and this notation is saying what's the total resistance from this circuit. This circuit appears to have exactly one path for electricity to flow, which makes it a series circuit. So we've got the total volts. We can find the total resistance, which we'll do first. In a series circuit, the total resistance is simply the sum of all the resistors. So we can get the total resistance by adding up the 470 ohms. The 1.2 kilo ohms, you want that to be in ohms as well. That's 1200 ohms, and that's 270. So the total resistance, if we were to add all of this up, we'd have 1670 plus another 270 is going to be 1940 ohms. So that's our total resistance. Now, now that we have the total resistance and we have the total voltage, we can use Ohm's law. Let's fill that in though. 1,940 ohms. We can use Ohm's law to find the total current. So Ohm's law is V equals IR. And you can use this formula with the total volts, total current, and total resistance, or you can go through and use this formula at a specific component. So right now we're going to use it for all the totals. The total volts is 10, the total current is unknown, and the total resistance is 1940 ohms. So to get the current total alone, we need to divide both sides by 1940. So 10 divided by 1940. And as the decimal, that is going to be 0.0005. I'll round to the fourth place value 2. And that's going to be amps. The values in the decimals do keep on going. I'm just going to round there, but that can change some other values. So that's total current. So 0.0052 amps. Okay, now that we know the current of the entire circuit, they're asking what is the current at each component. Well, in a series circuit, because there's one path for electricity to flow, that current must go through all the resistors, all these components. It doesn't have a way to branch off and go in any different direction. So the total current flowing of 0.0052 is how much current flows through each resistor, since this is a series circuit. So that's pretty easy. Alright, next they're asking for the voltage at each resistor. Well, at each resistor, so at R1, you can use Ohm's law. You can say the volts must equal the current times the resistance. And so we're going to do the volts at resistance 1 times the current at resistance 1 times the resistance of resistor 1. Okay, the voltage, we don't know. That's what we're going to look for. The current we just found out is 0.0052 through everything. And the resistance of resistor 1 is the 470 ohms. So we'll plug in our 470. So 470 times 0.0052 is 2.444. Now we can repeat that exact process for the other two resistors. So at resistor 2, we can have Ohm's law. The volts at resistor 2 equals the current at resistor 2 times the resistance of resistor 2. So again, the volts is what we're looking for. The current is our 0.0052. And the resistance of this one is the 1.2 kilo ohms, or 1200 ohms. So now we'll do 1200 times 0.0052, and I get 6.24 volts. Oh. Silly me, up on volts up here, for some reason I put ohms. You may have caught that already, but I'm just going to change that. Okay, and lastly, we want the volts at, slide this up, at the third resistor. So again, Ohm's law. The volts at resistor 3 is equal to current at resistor 3 times the resistance of resistor 3. So we're looking for the volts. The current is the 0.0052 amps. The resistance of this one is the 270 ohms. So now 270 times 0.0052 is 1.404. And that's volts. 1.404. Now, Kirchhoff's voltage law, KVL, is for a series circuit, says that the total volts in the circuit must be equal to, we would say, the voltage drop at each resistor. So there's a voltage drop. If you measure the voltage across this resistor, you get a voltage drop across here and across here. And those should add up to equal the total voltage. So let's confirm that. We know that, and this is really more of an equal sign. It's going to be, we've got the voltage of R1 plus the voltage at R2 plus the voltage of R3 is supposed to be equal to the total volts. So let's see. Total volts was 10. Is that going to be equal to 2.444 plus 6.24 plus 1.404? Well, 2.444 plus 6.24 plus 1.404 added up to be 10.088. Typing that exactly in. So, are they equal? They're off by a little bit, but we will say it's confirmed. Why am I off by a little bit? Well, when I went through and found all these voltages, remember that I used this 0.0052 current. That was rounded. That was a decimal that went fill up the entire screen of my calculator. And so it was just something that we needed to round at some point. Had I taken it out many more decimals and done my calculations, I probably would have gotten this to be closer to being exactly 10, but maybe still off a little bit, as what was on my calculator itself is probably a rounded value. So we will say that Kirchhoff's law is confirmed.